Welcome to another Protagonist Science video. In this first installation of the multi-part series, I want to talk about the foundations of transhumanism, the science behind brain-machine interfaces, and the very different notion of our shared humanity. What is it that makes us human? Is it our body, our mind, the way we function together in society? Maybe a combination of all of these. Or could there be a mystical part, a soul, a spirit, something science has not found yet and deemed implausible, which really defines who and what we are as humans? Philosophical questions about the human condition have been with us for many millennia, maybe forever. And although often considered outside the realm of what can be scientifically assessed, our perception of ourselves has always been shaped and limited by the knowledge of our times. This is especially true in the extraordinary times we live in today. The scientific method has provided humanity with a body of knowledge so vast, it not only fundamentally changes how we can see ourselves, it has also put into question what we are ultimately capable of becoming. Transhumanism is a loosely defined philosophical movement combining various ideas and concepts from human enhancement science, techno-progressivism, and posthumanism. Transhumanism has many roots, from ancient tales about immortality to various Enlightenment philosophers to works of science, fiction, and art. The foundational belief at the heart of transhumanism is an understanding of our body and mind as nothing more but a complicated biological machine, which can and should be improved upon with science and technology. Consider as analogy a computer system. Transhumanists aim to both upgrade the hardware of our bodies and the software of our brains to produce a better version of ourselves, however one wants to define the term. Conquering aging and death, uploading our minds into computers, replacing our body parts with machines are often conjured up as representative goals of transhumanism. Critics, myself included, often allege that proponents of transhumanism display characteristics commonly observed in cultists, a flock following a guru or a sort of techno-religion with their own eschatologies, where suggested events like the explosion of artificial intelligence and the singularity are hailed as the arrival of our new machine gods. It will not come as a surprise that many, if not all, of these extreme beliefs are as technically flawed as they are reflective of deep human desires. Yet scientifically, at least some version of these ideas stand on solid ground, and this is what we want to explore in this video. As science progresses and our capabilities expand, the boundary between what is possible and what is fantasy keeps shifting. In history, the line between science and science fiction has often been a blurry one. What was once considered pure fiction 100 years ago might well have become a mundane fact of today. Consider the following thought experiment. If you could talk to a person that passed 100 years ago and you would tell him about this magical device in your pocket which allows you to essentially access all of humankind's knowledge with just a swipe of your finger, would he have believed you? And what would that person have thought of you and your sanity if you then explained to him that you use this magical device mostly to look at videos of cats and start meaningless arguments with people you do not know and will never even meet? That person might have doubted a future like ours possible, and yet this is the new human condition we find ourselves in. Famous science fiction writer Arthur C. Clarke once proclaimed, "Any technology sufficiently advanced is indistinguishable from magic." One does not have to subscribe to transhumanist ideas to recognize that some of our recent scientific innovations might well be the building blocks to a technological future indistinguishable from magic. So today I want to introduce you to one of those building blocks. A brain-machine interface is any technology which allows humans to communicate or interact with an electronic device via thought. On the most abstract level, we can think of these interfaces as plug-ins into the wetware of our brain, either reading out and interpreting signals taken directly from the constant buzzing of our neurons, or inversely, adding electric signal impulses into the neuronal mix for our brain to process. Send electrochemical patterns in or read them out. Both approaches have shown remarkable success in recent years, especially in areas where disease or injury disrupted the biological function of neurons or nerve cells. Take spinal cord injury, a widespread and traumatic experience impacting the life and well-being of millions of humans around the world. Injuries to spinal segments between C4 and C7 are the main cause of tetraplegia, the loss of partial or total function of all four limbs. As of today, we cannot repair nerve damage to the spine, disallowing information to flow between brain and limb. But we can bypass the damaged neuronal wire, for example with a brain implant recording motor neuron activity and sending the signal via Wi-Fi to a pulse generator implanted on the spine downstream of the injury. We can also take the example of locked-in syndrome, a horrible paralysis where functional and conscious minds are forever imprisoned in mostly lifeless bodies, unable to communicate. An unspeakable nightmare for many, yet hopefully not a lasting one. Experiments and treatments are ongoing in multiple labs around the world, allowing patients to regain some way of communicating with the outside world by essentially reading their thoughts with brain-machine interfaces. This is science at its best, bringing hope and relief where we formerly only knew misery and defeat. If you want to understand these technologies deeper, you can check out this channel's video on pattern recognition and neuronal networks as well. Another area of research goes the opposite direction, using machines to collect the perceptions and sensations of the outside world and introducing them to the wetware of our brain through electric microstimulation. It turns out that our brain is not particularly picky when applying its natural pattern recognition algorithms. For as long as artificial signals are translated into the electrochemical patterns our brain can understand, our brain has no preference, no ability to distinguish nerve from electrode stimulation. Today, our electrodes are still not as advanced and fine-grained as neurons. Nevertheless, using artificial sensors or body parts and connecting them to the brain had remarkable successes. From restoring a sense of touch in tetraplegics to giving back partial vision in patients suffering from progressive blindness. If you have watched the Paralympics at any point in the last 5 years, you will also have noticed how prosthetics are increasingly well integrated with the athletes' bodies. Neuroprosthetics that can sense and transport information directly into the brain is just the next logical step. Already today, we can be confident that most paralytic disabilities will be treatable with brain-machine interfaces. Similarly, how deafness is already treated with cochlear implants. But this is not the end of the story. Today, brain-machine interfaces are mostly used to compensate for the loss of a specific function in our body, restoring communications to those who can speak, perception to those who can see, hear or feel, or movement to those who lost limbs. Yet neuroprosthetics could in theory also be used to enhance bodies beyond our biological limitations, introducing, for example, artificial sensors like magnetoreception or infrared vision by coupling the respective artificial sensors with a brain-machine interface. We don't know yet how our brain will learn to process these signals and project them into our consciousness, but we cannot confidently say it will be impossible to do so. Reversely, innovations in thought-based communication are not restricted to people who are unable to speak. Through brain-machine interfaces, much of our communication might in fact shift towards thoughts, including for tasks like navigating machines and browsing the internet, which currently needs our hands to type in commands into a visual user interface. At the moment, all brain-machine interfaces suffer from low efficiency, which makes them slow. The devices and strategies we currently employ are not yet sophisticated enough to compete with the typing speed or sensory nuance of our body. Because progress is fast and not always linear, we have a hard time predicting when certain milestones will be reached in that area. Nevertheless, what we can foresee is that all these brain-machine technologies converge towards a transhumanistic concept called morphological freedom, the understanding that once we can separate our brains or even our minds from the biological machine of our body, we are free to choose whichever machines we want to commandeer or inhabit. Already today, in the case of locked-in syndrome patients with a brain-machine interface, there is little technical difference whether their brainwaves are used to regain some mobility of their body through some neuroprosthetics, or whether these signals are used to navigate remote robotic limbs. Our future might in fact be closer to Avatar than the Matrix, or even a combination of both. Maybe there is no real difference between science and science fiction, but the factor of time. Most of us who are young today will get to find out. The future is neither deterministic nor completely random. It is shaped by our collective visions and actions. Transhumanist fictions often provide an avenue to ask big philosophical questions about ourselves, our future, and our role in the universe. Not every fiction can or will become reality, yet it would be unwise to pretend that our scientific innovations and our technological progress doesn't require of us to adapt to ever-changing circumstances and new possibilities. To exist means to adapt. Maintaining a rigid or fixed picture of humanity betrays the core of what makes us humans special in the first place. Our inborn curiosity, our passion for exploration, our hope for the future, and our will to collectively challenge the boundaries of our own limitations.